So we're going to skip ahead a little bit and then do chapter 13. Chapter 13 is gravity. Isaac Newton is often credited for his work with gravity. And he was thinking about how gravity works. And he says, okay, we've got Earth here and we got the moon out here. And knowing what he had already figured out about motion, the moon should go off in a straight line unless there's a pull on it. So there has to be some pull always on the moon. So as the moon's going around, there's always a pull on it. And so you're always pulling on the moon, and he realizes, okay, that's the pull of gravity. Okay, and so why, how does this work? And he starts thinking about this and said, well, if you're talking about, for example, someone standing here and twirling a mass around on a string around them, then you've got this centripetal force right here. So gravity must be making a centripetal force. It must be pulling on the moon. And so that means that everything's being pulled towards the Earth here. And so he starts thinking about this, and he thinks about it and thinks about it, and he says, well, we ought to be able to figure this out in some fashion, some relationship. And so what he does is he imagines, okay, you got the sun, you got the Earth. Well, the sun pulls on the Earth. That's why the Earth goes around the sun. So it's not just the Earth that has gravity. And then he starts thinking about it and says, well, it's got to work many different ways. Okay, for example, it's got to pull back. So Earth has to pull on the sun pulls on the Earth. Earth pulls on the moon pulls on the Earth. So he says, well, what's going on here? And he starts thinking about it a little further, and he says, well, for every force, there's an equal and opposite force. And so he begins to think about this and say, okay, we've got Earth here and we got some mass, and we know the gravity pulls down on it with a force mg. And he says, well, okay, so if for every force an equal and opposite force, okay, so he says, okay, so that means that it must pull upwards on Earth with a force mg also. And he says, okay, if I make the m bigger, it makes the force bigger. So somehow force is related to mass. And he thinks, well, mass must be this thing that's making the force, the gravitational force, so it must relate to the mass of the Earth as well. So if I make the mass of the Earth bigger, that would also increase the force of gravity. And so he starts putting all this stuff together. And he says, okay, if I have any two masses, m1 and m2, there's going to be a force of gravity between the two. Okay, same thing, he starts thinking about it. So there's always going to be, anytime you have mass, you're going to have gravity between the two. And he imagines, even in the space station. Well, he didn't imagine the space station, but if you imagine you put two astronauts in the space station, then what's going to happen is gravity is going to pull them together. It's not really zero G, it's what we call microgravity. So gravity is going to pull them together. Now, typically astronauts don't float together in the middle of the space station because you got air handlers, blowing fresh air around, in there, and that's exerting forces on them. They actually breathe, and when they breathe, they exhale, and that preserves forces, But imagine if you were to take the space station and open the airlock at the end of the space station. Okay, so you let all the air out, and then you put two dead astronauts into the space station, then gravity would eventually cause them to drift together. Okay, don't actually do that. But he starts thinking about this and says, okay, so we got mass 1, we got mass 2, and we want to have some force due to gravity between the two. So obviously, if mass 1 is bigger, then the force is bigger. If mass 2 is bigger, the force is bigger. So it's proportionate to mass 1. It's also proportionate to mass 2. Okay. Then he looks at it and says, well, what if I move mass 2 to a different spot? If I'm the same distance away, then I can just put my axis different, and I should get the same result. And so if I move it over here, I just put my axis like that, it should look just like it did in the first time. And so if I put the object down here, the axis, and if I swing it around to in front, it should be the same. So he starts realizing that this mass here is affecting everything equally on the surface of a sphere of radius r. Okay. And so if I stay the same distance away, I can put my axis there. There's no up or down in space, so it should make no difference. Then he says, okay, how does that work? What's actually doing this? And so he's thinking about it a little bit more, and he says, well, how does this actually work? Well, he starts thinking about it and says, well, we've got this mass right here. Okay, if you're some distance r away, okay, everywhere on the surface of that sphere, the force is going to be the same directed inwards. And then he says, now wait a minute, there's no actual physical connection between the two. Gravity is somehow exerting an effect all over the place out there. Okay, and so if you're a different r further away, you know that gravity is also going to be directed inwards. And so he says that's a new r, but you still have gravity directed inwards. So it's the same object in the middle exerting the same effect on space. And he starts thinking about it and says, well, this is as if it's creating a field of forces. In fact, we call this a force field. So this is the gravitational force field. At any spot in space around this object of mass m, there's going to be a gravitational field. So, and it's going to be directed towards there. And so he says, now, what's happening is, for any of these different spheres surrounding there, on the surface of that sphere, it's going to be the exact same force on that sphere. Now, it's not maybe not be the same as the force on another sphere. And he thinks about it and says, what's different? Well, this different spheres have different areas. So it is as if the force or the effect that's making the force is spread out over the area of a sphere. Well, we know the area of a sphere is 4 pi r squared. So if you double the r, you have 4 times the area. So if the effect is spread out over 4 times the area, you would expect 1/4 of the effect. So he says this equation must go as the inverse of r squared. Okay. And so now remember, the unit of mass is a pretty arbitrary sort of thing. We define kilogram arbitrarily. Likewise, a meter is arbitrary. Second is a pretty arbitrary sort of thing here. And so all these units are pretty arbitrary. Obviously, you don't really change the force when you change units. You just change the number. And so you'd have to have multiply by some constant that takes into account the 4 pi, the geometry space, takes into account your arbitrary units, and takes into account the strength of the gravitational force. So we give that a capital G. Capital G is Newton's universal gravitational constant. Okay. So this is Newton's universal law of gravitation. And that is that the force due to gravity is capital G times the two masses multiplied together divided by the distance between the centers of the masses squared. Capital G is a constant of nature. This is something that you cannot actually derive. It's something that you have to measure. And it's equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. So that's just a constant of nature. Was first measured accurately late 1700s by a fellow by the name of Henry Cavendish. And so that gives us the universal law of gravitation.